In this example, we have this simple car shed. It's like a butterfly shaped canopy. And we will now check the effect of unbalanced roof live load on this structure. Now, if we assign the area load and we assign the dead, the roof live load, the wind load, the typical loads, and we run the model, we will see that under the roof live load, for example, the balanced roof live load, that we have zero moment at the column due to equilibrium. Because these beams are identical, mirrored, the moment from the left beam will be countered by the moment of the right beam. So here we see that the moment is around 50 kilonewton meter, and the moment here is also 50 kilonewton meter. So the summation of moment at this joint is zero, and the column will only carry axial load. Now, when I assigned the roof live load case 2 unbalanced only to the left portion of the canopy, here's the first balanced case, and here's the unbalanced case. I can see that a huge moment will develop at the column, because now the counter moment will be developed at the column to counter the weight at the left portion of the canopy. Now I did add the combinations for the cases with balanced live load and for the cases with unbalanced live load with A. So let us now design without the unbalanced live load effect. We will remove the area, and we will see that the columns are very relaxed. They don't have any bending moment. For sure here, I'm not concerned about the optimization, but I want to show you the effect of the unbalanced live load on our design, especially for this type of structure. Now, when I add the load case for unbalanced live load, I will see that a huge moment value will be added. And here around 60% of the capacity of the column is due to bending, due to this moment value. So always you need to consider the unbalanced live load. Now, let us check the design of this base plate and clarify one of the common mistakes many engineers might fall for. Here, due to the presence of the live load of one side of the canopy, we will expect high rotation for this canopy. This rotation is due to the lateral displacement of the column and due to the deflection of the beam. So we have a lateral displacement of the vertical element and vertical deflection of the beam. This will result in rotation of the beam to column joint. So now, let us design this base plate on idea statica. So here I did take the beam and forces, and I did provide this base plate design, and it's passing all the design checks. However, one of the common mistakes is forgetting or ignoring the stiffness check, especially for cantilever columns or any sensitive structures to drift. For example, the cladding support, especially if we have brittle material like curtain wall, it's mandatory to check the stiffness of the fixed connections. This is also applicable to any moment connection or rigid connection modeled in our model. We need to check that it's designed as a rigid connection. It's not enough to consider only the design checks for plates, anchors, welds, etc. So here we did run the stiffness analysis. We will run again to show you how to do that. In idea statica, we apply the load and we will assign the length of the column. Here we have a 6-meter height column. We will reflect that and we will check the stiffness of the joint in the report. Here, the theoretical length of the column is 6 meters. Now we will go and check the report. Now, as we can see, the class of this connection is semi-rigid. Now, let us reflect this rotational stiffness in our model to check if it has any influence on the deflection or the drift of the column. Now, the secant rotational stiffness must be considered in the model. How to do that? We will go to the model. We will unlock the run. And now we will assign this rotational stiffness. We go to spring, and here in the global Y, we will consider a rotational stiffness equal to 7,100 kilonewton meter per radian. We multiply this number by 1,000. Here we have a mega newton meter. We convert it to kilonewton meter. So we have 7,100 kilonewton meter. Then we go to the restraints and we untick rotation about 2, local axis 2 of the joint. To be sure, we go and show the local axis for the joints. Indeed, it's local axis 2. And here we can see the pin support shape for rotation about the global Y or the local 2 axis. Now, let us run again, and we will now compare the deflection or the drift value with this modified rotational stiffness, the actual rotational stiffness as per the connection design, to the assumption of a rigid connection. Now, let's pick this unbalanced roof live load, which has the major effect on the rotation of the canopy. Here we have 160 mm lateral displacement of the column. Here we have around 225 millimeter as a vertical deflection for sure these values are high. Here we want to show the impact of the joint stiffness on the behavior of the structure. Now, we did adjust this connection to result in a rigid connection. We added some stiffeners. We increased the number of anchors for moment value around the major axis, and we will run the model again. We did not change the support reaction. Now we will check the stiffness of this joint. Okay, now we will check the stiffness. We can see that the class of this connection is rigid now. Now, as we have a rigid connection, it's enough to consider a rigid joint in the software without adding the actual rotational stiffness. So here we will remove the spring and we will assign a fully rigid base plate. Now we can see that the value of the column drift dropped from 160 mm to 114 mm. The deflection dropped to 189 mm. So there's a big change in the values for deflection and drift. Now, if we want to reflect the actual stiffness of the rigid joint from idea statica, we will take this value and we will reflect it in our model. Now we will replace this value. So this is now my rotational stiffness for the rigid joint. And we will remove the restraint for rotation around local axis 2. We will see that the lateral displacement of the column is close to that a totally fixed base plate, 116 to around 180 millimeter. Also, the deflection of the beam is close. So now, this gives us the confidence of considering a fixed support for the column is a valid option, and it's practical to only use the fixed base plate when we have a rigid joint stiffness. We don't need to do the extra step of reflecting the actual rotational stiffness, the secant rotational stiffness, to get the actual value. This will lead to a prolonged design, and that's not needed. However, if we have a semi-rigid classification, we need to consider that in our analysis model. Most of the time, we might need that to capture the actual behavior of the structure. So keep this in mind.